Hello, everybody. In the previous lecture, we have finished the first topic of the second part of this course, charge carrier concentration. We related it to the concentration of ionized donors and acceptors. We have realized that at room temperatures and in a broad window around the room temperature, all or almost all of your impurities, shallow impurities, are ionized. But we did all this discussion under the tacit assumption that there is no electric field acting in the semiconductor, that the electric potential is uniform. We set the value of the electric potential to 0, but it doesn't matter which value we would set the value of the uniform electric potential as long as it is uniform. So now we will moving on to the slightly more complicated situation when there is an electric potential in the semiconductor and that electric potential is non-uniform, so there are electric fields in the semiconductor, but the semiconductor is not part of a closed circuit, so there is no current flowing in the semiconductor. There is merely a redistribution of electric charges, electrons and holes in the semiconductor induced by this electric field, so that the net electric field in the semiconductor is 0. So somehow you impose an external electric field and it superimposes with an internal electric field due to the redistribution of your mobile charge carriers, electrons and holes, so that the net electric field in the semiconductor is 0. So that's what we will be discussing, and this and in the next 2, I think, lectures. In this lecture, I will start with Gauss's law. I know that most of you have already read about Gauss's law or took a course in general physics where Gauss's law has been discussed extensively, but repetition is the mother of learning, so let us begin with Gauss's law. Gauss's law relates electric field to the charge density. All right, then I will introduce the differential form of Gauss's law, known as Poisson's equation. It is equivalent to Gauss's law, but it is written in the form of a differential equation. Then I will apply Poisson's equation to a semiconductor where the charge density is due to electrons, holes, and also ionized donors and acceptors. So Poisson-Boltzmann's equation can be solved. So we will discuss the solution of Poisson-Boltzmann's equation in the next 2 lectures. And but in this lecture, I will conclude not with the solution of the Poisson-Boltzmann's equation, but with the discussion of band bending near the surface of the semiconductor if a surface potential is different from the value of the electric potential in the semiconductor bulk that is far away from the surface. So that's the plan. All right, Gauss's law. And repetition is the mother of learning. So let us go even to even more fundamental things. Let us discuss Coulomb's law. Let's say you have a single point-like charge Q, as red dot at the origin of the coordinate system is the point charge Q. Yes, okay, so it sits at the origin. It produces electric field. The electric field produced by a point charge is given by this famous formula. It is directed radially, so r hat is a unit vector in the radial direction. So the direction of this unit vector r hat depends on which point you are looking at. And it always points away, r hat always points away from the origin where your charge Q is located. The magnitude of the electric field is proportional to the charge Q itself and inversely proportional to the distance squared from the charge, so Q over r squared. The proportionality constant in T units is the Coulomb's constant, 9 10 to the 9th, approximately, to 1% accuracy, 9 10 to the 9th Newton meter squared per Coulomb squared, if my memory is correct about the units. Yes, F is K Q squared over R squared. Yes, so Coulomb's constant is written as 1 over 4 pi epsilon naught, where epsilon naught has the value of 8.85 10 to the negative 14th farads per centimeter, or 8.85 10 to the negative 12th farads per meter. It is called the electric permittivity of vacuum. And it gets multiplied with the relative dielectric constant of the material, epsilon, or relative permittivity of the material, epsilon, which in semiconductors has the typical value of the order of 10, give or take. All right. All right, so that's our favorite Coulomb's law. Now, let us define the concept of the electric field flux. You consider a closed surface around the charge. And the electric field can be represented as electric field lines. Those electric field lines go through that surface. The flux of the electric field is, roughly speaking, it is proportional to the total number of the electric field lines that penetrate the surface around your charge. So this is a very loose, hand-waving-like definition of flux, not even a definition, explanation of flux. But now here is the definition. So you have some closed surface. In principle, the surface does not need to contain the charge, but let's say it is around the charge. The important thing is that the electric field lines go through the surface, traverse the surface. You divide that surface into small patches. Each small patch has the area dA. You multiply, you take the dot product of the dA area vector with the local value of the electric field. And by local, I mean you measure the electric field at the same point where that patch is located, where the dA patch is located. So you take the dot product of the two vectors, dA and the electric field, and you take the sum over all patches that cover your surface. In the limit, the area dA goes to 0. The sum becomes an integral, and that integral is the flux. Now, the direction of the dA area vector is, by convention, adopted universally, is outward, not into the surface, not inside, but outward direction. All right. So that's the definition of the electric field flux in the most general form. Now, in particular, we can choose the Gaussian surface to be a sphere around the charge. The charge is located in the center of this sphere. Now, the reason why we chose the Gaussian surface to be a sphere is because first, the electric field has produced by the charge has a constant magnitude everywhere on that surface, on the sphere, because the distance from any point on the sphere to the center of the sphere where your charge is located is the same. So the electric field is the same. And second, the electric field is tangential to the surface of the sphere at every point. So the dot product of the surface area dA, infinitesimal surface area vector dA, and the local value of electric field is just the product of their magnitude. For this choice of the Gaussian surface, you can take, since the electric field is constant everywhere, and dA dot E vector is the same as dA scalar multiplied with E scalar, you can take the electric field outside of the integral. It is constant everywhere. And all you need to do is to integrate the is to take the surface integral over the area of the sphere. Of course, the area of a sphere of radius r is 4 pi r squared, and the electric field is given by Gauss's is given by Coulomb's law, q over 4 pi epsilon naught epsilon r squared. Now notice that this 4 pi r squared and this 4 pi r squared in the denominator of the electric field mutually cancel, which means that the flux through the sphere is the ratio of the charge inside the sphere divided by epsilon naught epsilon. And this is Gauss's law for a particular case when the charge is a point charge and the Gaussian surface is a spherical surface. But what if your surface is not spherical? Well, the result will be the same. The flux through any surface around the point charge Q is the same as the flux through a spherical surface, which is independent of the radius of the sphere, Q divided by epsilon naught epsilon. And the reason is very simple. The flux is proportional to the number of electric field lines through a closed surface. Every field line, now imagine two surfaces. One is the spherical surface and the other through which, the spherical surface through which the flux is known, Q over epsilon naught epsilon. And the other surface is a surface of arbitrary shape around the charge Q. Every field line which goes through the spherical surface also goes through the surface of arbitrary shape S, which means that the fluxes through the two surfaces are the same. If a charge Q is outside of a surface, any surface, not just spherical, then it produces zero flux through that surface, closed surface, of course, I mean closed surfaces, zero flux if the charge is outside of the surface, because every field line which enters the surface will also leave the surface, or the region surrounded by the inside that surface. Another statement, the last statement that I would like to make is, what if the charge is not a point charge, but maybe we have a bunch of charges, maybe we have a bunch of charges distributed somehow uniformly or non-uniformly in space. There is some sort of a continuous charge distribution. Well, in that case, nothing changes essentially because of the superposition principle. The electric field produced by a bunch of charges is the vector sum of the electric fields produced by each charge individually. Hence, the electric field flux produced by a bunch of charges is the sum of fluxes produced by each charge individually. And that means that the total flux through a closed surface equals the ratio of the total charge inside, enclosed by that surface, divided by the electric constant of the material, epsilon naught epsilon, in the medium in which those charges are located. So this is our Gauss's law. Hooray. Now so this Gauss's law defines the electric field flux as an integral characteristic, right? As a surface integral. Poisson's equation is a differential form of Gauss's law, and I will explain Poisson's equation in the one-dimensional case only, because it is the three-dimensional cases only slightly more complicated, but one-dimensional version of Poisson's equation is all that we will ever need in this course. So here goes. Suppose your electric charge is characterized by volume charge density rho, and that volume charge density, that is how many coulombs of charge is in 1 cubic centimeter unit volume. This volume charge density is non-uniform, but it changes in the x direction only. So it doesn't change in the y or z direction, it changes in the x direction only. By symmetry, it is clear that the electric field produced by this non-uniform volume charge density, rho of x, should also be directed along the x-axis in the x direction. So Poisson's equation that we are about to derive tells us, relates the charge density rho to the electric field and to the electric potential generated or produced by this non-uniform charge density rho of x. Let us choose our Gaussian surface in the form of a slab, a thin sheet of material. Of course, Gaussian surface is an imaginary surface, so you do not really need to cut that slab out of the material. You just imagine that surface. So imagine this thin slab of thickness delta x. The electric field on the left surface of the slab is E of x, and on the right surface of the slab it is E of x plus delta x, or dx on the picture, but later we will take the limit delta x goes to 0, so we will convert delta x into an infinitesimal thickness dx. All right, so once we know that, pretend to know the values of the electric field on the left and on the right surfaces of the slab, we can figure out the electric field flux through the slab. It is the, let us assume that the electric field points in the positive x direction. So the electric field flux through the slab is the electric field flux through the right surface, plus the electric field flux through the left surface. The electric field flux through the right surface is E of x plus dx. The electric field on the right surface times the area of the slab, A. The electric field through the left, and notice that both values, E of x plus dx or delta x and A, enter with the same sign, because so we assume that the electric field points in the positive x direction. If it points in the negative x direction, then you just have to change the sign of E of x, or E of x plus delta x. Okay, and the area vector on the right surface also points in the positive x direction, that is outside, outward. Now the contribution to the electric field flux from the left surface is minus negative E of x, x is the position of the left surface, times the surface area. So, and the minus sign here is because the electric field on the left surface still points in the positive x direction, but the area vector on the left surface points in the negative x direction. So the angle between the two vectors is 180 degrees, and cos of 180 degrees is -1. All right. Now, by Gauss's law, we know that the flux of the electric field through this slab is the ratio of the total charge inside the slab to the dielectric constant of the material, which is the product of the electric permittivity of vacuum epsilon naught, and the relative dielectric constant or relative permittivity of the material epsilon. The charge inside the slab is the volume charge density times the volume of the slab. The volume of the slab is the surface area times the thickness delta x. All right, so we have this identity, and we see that the surface area multiplies both the left-hand side and the right-hand side of this identity, so we can divide by the surface area. Then we can divide by delta x and take the limit delta x goes to 0, in which case we will have E of x plus delta x minus E of x divided by delta x, which in the limit delta x goes to 0 becomes just the derivative of the electric field dE by dx. In the right-hand side, we will get rho of x, so the local charge density, divided by epsilon naught epsilon. Now we recall that, so this is already Poisson's equation. Now let's write it in a slightly different form. recalling that the electric field is the negative derivative of the electric potential, minus d phi by dx. So the second derivative, plug in this value, this electric field expressed in terms of the electric potential into dE by dx into the left-hand side. We find that the second derivative of the electric potential with respect to the coordinate x, d2 phi by dx squared, is negative charge density rho of x divided by epsilon naught epsilon. That's in one dimension, and this is all that we will need in this course. But in 3 dimensions, Poisson's equation is essentially the same, only the second derivative with respect to x becomes the Laplacian. So it becomes the sum of the second partial derivatives with respect to x, y, and z. So d2 phi by dx squared plus d2 phi by dy squared plus d2 phi by dz squared equals minus rho of r. R is the local coordinate, local position, where you're evaluating the charge density and the second derivative of the potential as well, divided by epsilon naught epsilon. Okay, so now we have our Poisson's equation. Now, let us apply Poisson's equation to a semiconductor. Specifically, the situation in which we will be interested is that the semiconductor is half infinite, or it has large but finite thickness. Large but finite thickness. And on the surface, somehow the value of the electric potential is phi sub s. Surface value of the electric potential is known, we assume to be known, phi sub s. And far away from the surface, the semiconductor is grounded. So in the bulk phi of infinity, by infinity I mean large but finite distance from the surface, the semiconductor's potential has the value 0. It is grounded. And we are interested in how the electric potential changes from the surface value phi surface to the value 0 far away from the surface. Now, because the semiconductor is somehow we can, for example, apply an external electric field, which will induce a particular value of the surface potential on the semiconductor. This is really done in metal oxide semiconductor structures, in MOSFET transistors. The semiconductor is not a part of a closed circuit, so no current is flowing. The charges just redistribute themselves in space, but once this redistribution of charges results in vanishing of the electric field inside the semiconductor. And once the electric field inside the semiconductor is 0, then the redistribution of the charges stops. Okay. So, and this is the situation in which we are interested. All right, so now let us write down the expression for the charge density in our semiconductor, rho of x. The charge density is due to 4 types of charges. We have 2 types of mobile charges that are free to move in the semiconductor. These are electrons and holes. And we have 2 types of stationary charges, which are ionized donors and ionized acceptors. So electrons and acceptors are negatively charged particles, and holes and donors are positively charged particles. Multiply the volume, the concentration of each type of charges with the elementary charge, you will get the respective volume charge density due to that type of particles. So the charge density is the elementary charge times the sum of concentrations of positive charges, donors, ionized donors, and holes, and minus the sum of concentrations of the negative charges, which are acceptors, ionized acceptors, and electrons. So this is our charge density in the semiconductor. And now we plug in this charge density into the Boltzmann's equation. And also we need to relate the electron and hole charge densities to the local value of the electric potential. Now, of course, donor concentration and acceptor concentration are not affected by the electric potential because the ionized impurities, they just sit in the lattice and they do not move anywhere. They do not redistribute themselves when an electric field exists in the material. Only the electrons and holes have the ability to redistribute themselves. All right, so we derived, a few lectures ago, we have derived an expression for electron and hole concentrations when there is no electric potential. It is the density, the effective density of states, and for example, for electrons, it is the effective density of states at the bottom of the conduction band times the probability for a particular state and at the bottom of the conduction band to be occupied, and that probability is given by Boltzmann's factor exponential to the power minus EC, the energy at the bottom of the conduction band, minus the Fermi energy, divided by KT, the thermal energy. If the local value of the electrostatic potential phi of x is different from 0, the energy of the electron is reduced by the product of the elementary charge times the value of the electrostatic potential. So if EC is the energy of the electron at the bottom of the conduction band, this needs to be replaced or shifted or biased or offset by this value of the electrostatic energy of the electron. So EC becomes EC minus elementary charge E times the electric potential phi of x at a given point x. So now notice that exponential to the power minus EC minus E Fermi over KT times the effective density of states is the electron concentration without the electric potential. And I call it N naught sub B. N naught sub B. B stands for bulk. And by bulk, I mean the point far away from the surface where the electric potential has the value 0. So somewhere here is the bulk. Far away from the surface where the electric potential has the value 0. So the local value of the electron concentration is the bulk value, and not sub B times exponential to the power phi of x divided by the thermal voltage V thermal. V thermal is the ratio of the thermal energy KT to the elementary charge E. And of course, the reason why I will prefer to use the thermal voltage here instead of the thermal energy KT is because the letter E would be overloaded. It will have two different meanings. One would be the basis of the natural logarithm. It's 2.718 or 9, or I forgot the remaining significant figures. And the other meaning of the letter E would be, of course, elementary charge, which is also conventionally, it is also a convention, elementary charge. And of course, this is the point when I regret that we physicists do not use Chinese characters. There are not millions, of course, but of Chinese characters, but tens of thousands of Chinese characters, and we would not have that problem of having the same symbol. Latin alphabet has 26 letters, so the problem of having the same symbol with different meanings would not be there. Anyway, so in order to avoid this duplication of E, I will be using, instead of thermal energy, I will be using thermal voltage, which is the ratio of thermal energy to the elementary charge, KT over E. All right, now notice that electron concentration at a point x is bulk concentration times exponential to the power plus phi of x over the thermal voltage V thermal. This makes sense. Electrons are negatively charged. They are attracted to positive regions, to the regions where the electric potential is positive. So the higher the electric potential, the higher the electron concentration. As for holes, we use the same idea. So the general expression for hole concentration, which was derived previously, was NV, effective density of states at the top of the valence band, times exponential to the power EV minus E Fermi over KT. EV is the energy at the top of the valence band. This needs to be offset by the energy of an electron in the presence of an electric potential phi of x. So we need to subtract E phi of x, and we recognize that NV times exponential EV minus E Fermi over KT is the bulk value of the hole density concentration P naught B, and it gets multiplied by exponential to the power negative phi of x divided by V thermal. Okay, the negative sign makes perfect sense. Holes are positively charged quasi-particles. They get repelled from the regions where the electric potential is positive. So attracted to the regions where the electric potential is negative. Also notice that there is this, I keep the subscript 0 in the electron and hole concentrations because there is no current flowing, so the system is still in equilibrium, which means that the Fermi energy is the same. It is uniform. No current is flowing, means that the Fermi energy is uniform everywhere in the material. All right, so with these expressions for the electron and hole concentrations, my Poisson-Boltzmann's equation assumes this form that may look a little bit intimidating. I mean, it is a second order ordinary differential equation, second order, second derivative with respect to x. It is nonlinear in the sense, the standard sense of the word. That is, the sum of two solutions of Poisson-Boltzmann's equation is not a solution of the Poisson-Boltzmann equations. The linearity property is not fulfilled. And so, like I said, this equation may look a little bit intimidating, yet it can be solved analytically, and we will discuss the analytical and the useful approximate solutions of the Poisson-Boltzmann's equation in the next two lectures. But today, we have 2 slides left. Let us discuss the band bending. So let me remind you that the energy band diagram is a graphic way of representing the important energies found in the semiconductor. So typically this would be the energy at the band edges, the Fermi energy, the intrinsic Fermi energy. How these energy levels change with the spatial coordinate x. Now the energy band diagram does not need to be precise in terms of the distances between the various energy levels, but you do need to be qualitatively correct. So if it is a p-type semiconductor, then your Fermi energy must be closer to the valence band. And if it is an n-type semiconductor, the Fermi energy must be closer to the conduction band. All right, in the presence of an electric potential, the energies at the band edges, EC and EV, become offset by the product of the elementary charge times phi of x, and because electron has negative charge, this offset enters with the minus sign. And now, if the electric potential is non-uniform, the energy at the band edges it bends. The band edges are not represented with straight lines anymore. It will bend somehow up or down. All right. So here are some examples. Let's say your surface potential is positive. If the surface potential is positive, then the term negative E times phi surface becomes negative, so the bend near the surface need to bend down. So this gray area is the surface of the semiconductor. This is where the semiconductor ends. So the bends need to bend down. Far away from the surface, the electric potential goes to the value 0. So the band bending has finite extent in space. Let's say the surface potential is positive. So the bands bend down, and if the semiconductor is of n-type, then in the bulk, the Fermi energy is closer to the conduction band energy than to the valence band edge energy. For positive surface potential, the semiconductor is of even more n-type. The concentration of electrons near the surface is even higher than in the bulk, which makes sense, right? If the semiconductor is of p-type and the band bending is not big, then the semiconductor may remain of p-type also near the surface, or because the band bending is not too high. If the band bending is not too high, but the concentration of holes near the surface will be smaller than in the bulk. But it doesn't need to be like that. If the band bending, that is, if the surface potential is large, then the Fermi level near the surface can be closer to the conduction band than to the valence band, even though in the bulk the semiconductor is still of p-type. But near the surface, you can have the situation when the Fermi level is closer to the conduction band than to the valence band, which means, due to the band bending, which means that conductivity inversion happens near the surface, and the semiconductor near the surface becomes of n-type, whereas in the bulk it is of p-type. This principle of conductivity inversion is used in metal oxide semiconductor field effect transistors, which we will be discussing in the third part of this course. The case when the surface potential is negative is treated in exact same manner, and I suggest that you draw these energy band diagrams for N and P-type semiconductors with negative value of the surface potential, which means that the energy bands are bent up near the surface. So that's all for today. Thank you all very much for your kind attention. I will see you in the next class. Bye-bye.